Welcome friends. Today we will discuss about the reaction mechanism of aldehyde and ketone. So far the NEET, the JEE Mains or Advanced is concerned, many questions used to come from this chapter, from this topic. The reaction mechanism of aldehyde and ketone is very crucial and very important. So let us quick begin about the reaction mechanism. There are a few types of reactions in aldehyde. We will first discuss in the earlier video, we have discussed the reaction of preparations of aldehyde or ketone. But today we will discuss the reaction of aldehyde. Now there are a few types of reaction, like number one, the oxidation. The oxidation of aldehyde. The oxidation of aldehyde, that is RCHO, under the effect of K2Cr2O7 and H2SO4, which gives nascent oxygen and forms RCOOH. That means carboxylic acid. Second of all, there are two types of reduction. One is with lithium aluminum hydride. It's a strong reducing agent, or sodium amalgam, the combination of sodium and mercury. As you said, as you see this picture, here the nascent hydrogen or here the nascent hydrogen, they are the strong reducing agent and they reduce the aldehyde group into 1 degree alcohol. So always remember the fact that the aldehyde on reduction with strong or mild reducing agent always gives 1 degree alcohol. On the other hand, if we use Zn amalgam or zinc amalgam along with HCl, it's called Clemenson reduction. As we know from the earlier chapters, the Clemenson reduction always gives rise to alkane. So this is name reaction, Clemenson reduction, and it forms RCH3. The whole lot of the CHO group will be, the oxygen will be oxidized to H2O and the whole RCHO group will become RCH3, that is alkane. So there are two types of reduction. One is Clemenson reduction and another is 1 degree alcohol. Always the aldehyde gives 1 degree alcohol, while the ketone always gives on reduction with the same reagent, lithium aluminum hydride or sodium alcohol or sodium amalgam, whatever, it will give 2 degree alcohol. This is the rule. It never skips, always follows. Number third, as you see in number 3, there is some nucleophilic addition. What I have said, the nucleophilic addition, or that means some nucleophile will attack the RCHO group. The nucleophiles are as HCN. It dissociates into H plus and Cn minus. The Cn minus being nucleophile will attack, like here the under resonance this electron comes to oxygen and here comes the positive tail of carbon. The Cn minus attacks this positive tail of carbon and forms like this RCCN. The H remain intact and the O with a negative charge. Later on, the H plus comes with this O minus and forms subsequently RC OH, Cn and H. Again I will mention the R, COH, H and Cn. Here it is the chiral center. Here it is the chiral center means it is asymmetric carbon and it is commonly called as cyanohydrine. So this is cyanohydrine with HCl. Ketone also gives the cyanohydrine, but in case of ketone, it cannot form the chiral center. So number 1 is cyanohydrine. Number 2 is NaHSO3, which commonly gives bisulfite compound. Things are like this: RCOH, just like the previous one. At first the O will come to O negative del, and then the H plus of the NaHSO3 will attack the O minus to form OH, and SO3H comes as nucleophile. So this is negative del, the carbon becomes positive del and the H remain intact. It's called bisulfite compound. So what I have mentioned, it is called bisulfite compound. Both the ketone and aldehyde gives bisulfite compound. No alcohol, no acid gives this bisulfite compound. But the ketone and aldehyde, as both have this carbonyl corner, both will give this bisulfite compound. And the third one is NH3. Here NH3 will form NH2 minus and H plus. This NH2 minus is actually the nucleophile, and subsequently it forms R O minus, which combines with H plus to form OH. The H remains intact and the NH2 part sits here as negative del and carbon is positive del to form aldehyde ammonia. However, this aldehyde ammonia is different in case of formaldehyde. So this aldehyde ammonia is different in formaldehyde. I am writing here the aldehyde compound. It is like this: RCO, O comes here, the oxygen, over the oxygen the electron comes here, the H here, the NH2 minus ion attacks the positive del of carbon and forms RCO minus, H stands here, NH2, and later on the H part of ammonia attacks the O minus to form the subsequently OH. So here the total aldehyde ammonia is here. The reaction is very slow, but in case of formaldehyde, in case of only formaldehyde, as I have written here, in case of only formaldehyde, it forms eurotropin. The formula goes CH2 whole 6N4. So this is the eurotropin, CH2 whole 6N4. So eurotropin is the exceptional reaction of aldehyde with formaldehyde other than any aldehyde. Any aldehyde cannot form the formaldehyde, but only formaldehyde will form with ammonia. This complex structure is called eurotropin. But other all aldehyde will undergo this aldehyde ammonia compound, this aldehyde ammonia compound. So here we see that all the nucleophile are being attacking the carbon part of aldehyde being positive tail. And these are nucleophilic addition. Now remember this fact that in nucleophilic addition, if the nucleophile attacking the RCOH group, here the nucleophile is attacking the carbon del, here del positive, here the nucleophile is attacking because here it is a lighter group H. Now for lighter aldehyde it will attack faster because it can sit here, their accommodation space is available for nucleophile in aldehyde. So formaldehyde will give this nucleophilic addition is very high, but in case of higher aldehyde it will be slower down because the nucleophile cannot sit or cannot have the adequate accommodation here due to this bulkier R group. So increasing the R group, the nucleophilic addition will be less. More the R group bulkier, less will be the nucleophile attacking over carbon tail. So it is very clear that it is called steric hindrance. So under this steric hindrance, lighter aldehyde first, then comes bulkier aldehyde, then comes bulkier aldehyde, and then comes lighter ketone, where ketone has this 2R group. Remember, here there was a light group H. Here no light group H is present. As a result, there is steric hindrance, that is the nucleophile cannot adequately attack the carbon tail positive part because less accommodation is there. So steric hindrance increases. So lighter ketone, in case of lighter ketone, some nucleophilic addition is going on, but in case of higher ketone, it will be lesser. So at first the greatest will be the lighter aldehyde, then it will be the bulkier aldehyde, then will be the lighter ketone, then will be the higher ketone. So it is highest and it is lowest. Never ever think that here the alpha H is greater or here the alpha H is greater. So the carbon tail positive will be neutralized by R group. It is not that fact. It is the fact about the steric hindrance. So we have talked something about the nucleophilic addition. Nucleophilic addition, after this nucleophilic addition, we are coming to different zone, that is reaction with halogen, like number 4 RCHO reaction with PCl5. Now PCl5 always breaks into PCl3 and Cl2. Now this O part will combine with PCl3 to form POCl3, that is phosphorus oxychloride, and the remaining 2 chlorine will attach to these 2 bonds of the carbon to form dihaloalkane. So this is the dihaloalkane. This is 1,1-dichloroalkane. So here another reaction, that is 1,1-dichloroalkane. Number 5 is reducing property. Only aldehyde has reducing property. What are the group of reducing property? That is this aldehyde group. Aldehyde group always reduces the combination of AgNO3 and NH3. These 2 react to form Ag2O. So that is silver oxide, which the oxygen taken up by the aldehyde and silver precipitation takes place, and aldehyde oxidizes in other term to form acid. It is called silver mirror precipitation. Silver mirror precipitation of metallic silver, and it is called toluene reagent. The combination of AgNO3 and NH3 is called toluene reagent. Now, no aldehyde, other than no aldehyde, no other group will reduce this toluene or phenylene or any other reducing agent. Now, they are reduced itself and the aldehyde will be oxidized to acid. Now we can take a look of like this structure. Here it's a cyclic structure, here it's a aldehyde. Now how will you convert it into acid? Only one good reagent is there, that is silver nitrate and NH3. The aldehyde part intact will go to acid with the silver mineral precipitation. Clear? So reducing property, after we will have a quick look over the water diluting reaction of aminated derivative. What are the aminated derivatives? Are the aminated or ammoniated derivative. As I have written here, ammoniated derivative means number one, there is hydrazine, it is called hydrazine, it is called hydroxylamine, it is called hydroxylamine, it is called NH2NH.C6H5. This is the phenyl group, so this is called phenyl hydrazine. And lastly, this is semi-carbazide, NH2.NH, and intact one amide group, that is semi-carbazide. What I have said is semi-carbazide. Now all those have some amine group. Now remember the fact that the aldehyde group is acidic and the amine group is alkaline or basic. So technically here the hydrogen with oxygen gives water. All the reaction will give water. So subsequently at first the reaction will be RC, the double bond will be intact, NH2 and the H remain constant. Here it is called hydrazone. Whenever it will react with ketone or both ketone and aldehyde, it will form hydrazone. In case of hydroxylamine, the RCH double bond intact, the H2 combines with the O similarly to leave one H2O to form RCHNOH. It is called aldoxine, and in case of ketone it is ketoxine. In case of phenyl hydrazine, it is very easier to know that RCH double bond, the H2 part being removed, the N.NH C6H5, it is called phenyl hydrazone. And the last one is RCH double bond. RCH double bond, the H2 part combines with the aldehyde oxygen part to form water. So all the water leaving reaction, and here it will form semi-carbazone, that is N.NH-CONH2. It is called semi-carbazone. Now if you ask me that which reaction is the identical reaction or exclusive reaction of aldehyde, the exclusive reaction of aldehyde is reducing property. You can see in any book that it reduces three reagents. One is toluene, as I said, that is AgNO3 and NH3. Another is Fehling solution. The Fehling solution is a mixture of sodium potassium tartarate and copper sulfate. So the net Fehling 1, sodium potassium tartarate, Fehling 1 and Fehling 2. The Fehling 2 is copper sulfate and Fehling 1 is sodium potassium tartarate. Both leads to COO actually. And number third is actually the Schiff's reagent. So Schiff's reagent is another reducing reaction. These three reactions here, Cu2 while red precipitation occurs, and we can distinguish red precipitation Cu2. I am writing here again, the failing will give Cu2 red precipitation, and in turn the aldehyde will form RCOH. Clear? So sixth reagent, failing solution and silver nitrate or ammonia combination toluene will be silver mirror precipitation. This reducing property are the exclusive property of always the remarkable property of aldehyde. That is why aldehyde has reducing property but ketone does not have. Remember, aldehyde have the RCHO. This H is responsible for any reducing character of aldehyde. I am writing here the H. I am particularly showing the H which is responsible for the reducing property. So these are the reactions for which we can distinguish with any ketone to aldehyde the reducing property. And another one is canizaro and aldol. Canizaro and aldol will be discussed the mechanism in the next class, but the canizaro and aldol overall is RCHO or only the HCHO being formaldehyde in OH medium. Let's say this is NaOH. Two molecules of aldehyde here, one molecule aldehyde undergoing oxidation to form formic acid and subsequently the salt of the formic acid, that is sodium formate, and another molecule of aldehyde, that is formaldehyde, will reduce to methyl alcohol. So one aldehyde simultaneously undergoing oxidation to formic acid or formic acid salt, that is sodium formate, and another aldehyde undergoing reduction to form methyl alcohol. So it is technically a disproportional reaction. What is disproportional reaction? Disproportional reaction is the simultaneous undergoing the oxidation and reduction of the same atom. Here's the same atom, carbon, simultaneously oxidizes to acid and simultaneously reduces to alcohol. So this is the canizaro. But the exact mechanism will be discussed in next class. In case of aldol, here in canizaro reaction, it is the canizaro reaction, and in case of acetaldehyde, as in case of canizaro reaction, the condition is no alpha H. Here you can see that here is no alpha carbon and no alpha H. So condition is no alpha H should be present. So alpha H technically, alpha hydrogen technically will be absent. But in case of CH3CHO, it is called aldol condensation. At first, this part, two molecules of acetaldehyde is there in presence of OH minus medium, and here the one part being CH3, CH2, CO. Here the oxygen takes the double bond of the electron and becomes negatively partial positive negative charge, and the hydrogen is here, and another one here is CH2CHO. CH2CHO negative tail. How it possible? Because another aldehyde gives off the H plus, alpha H plus, and the alpha H plus ultimately attacks, the alpha H plus attacks with the OH minus medium, to form water. So here it is negative tail and here it is positive tail. The electrostatic attraction between the two aldehyde will combine to to form CH3, CO minus, H, CH2 and CH2. Later on, this H2O will firstly H plus dissociate into H plus and OH minus. So technically the OH minus remains into the medium. Technically the OH minus remains into the medium and the H plus attacks into the O minus charge. The H plus attacks into the O minus charge. So what I have gone through, that the alpha H of one aldehyde attacks actually the OH minus ion, or OH in turn attacks the alpha H, and the remaining carb anion will attack another aldehyde's carb cation by electrostatic force of attraction to form new carbon-carbon bond. So there is new carbon-carbon bond. So here the H attack, the H plus ion attack over O minus becomes, this is functional group, this is alpha H and this is beta H. So this is beta carbon and the overall component is called beta hydroxy compound. So CH3, CHOH, CH2 and CH is called beta hydroxy compound. This beta hydroxy compound, it is alpha and it is beta. This beta hydroxy compound is very much unstable and ready to shed off one water molecule. That is, they are very much prone to dehydration, and as a result, taking one alpha H here, it leaves one water molecule. As a result, between the beta and alpha H, there is some double bond. Unsaturation takes place and forms CH3, CH, double bond CH. So here it leaves one water molecule. So beta hydroxy compound is not final product of the aldol, but it is called aldol. Now aldol subsequently undergoes dehydration to form CH3, CH, double bond CH. This is beta and this is alpha. So this is called alpha beta unsaturated aldehyde, and technically this aldehyde is called butyl enal, or the general name is croton aldehyde. So general name is croton aldehyde. I am writing here again the mechanism. Here the compound name is croton aldehyde. So these are the general properties of aldehyde and ketone. I have already discussed it in very limited segment, but in detail, particularly the aldol, the canizaro, and particularly these two and acetal compound will be discussed in our next class. So this was a class about the aldehyde general reactions. I have not gone to aldehyde, acetaldehyde or formaldehyde. I have only talk about only the acetaldehyde, not generalized aldehyde, not acetaldehyde or formaldehyde. Yes, I have told that formaldehyde causes eutropine or acetaldehyde forms croton aldehyde, but these are the not reactions of aldehyde, acetaldehyde, formaldehyde exclusively. This is the generalized properties of aldehyde, but these are the mechanisms which we have to understand very in detail. These three reactions in detail in our next class, that is canizaro and aldol reaction, so that we can go to ketone. For that, unto that time, my classes is going to end, and we'll see in part 3 of aldehyde and ketone.